Hello, we're gonna talk about motion of a charged particle in uniform magnetic field. The magnetic force acting on a charged particle moving in a magnetic field is perpendicular to the particle's velocity, and consequently the work done by the magnetic force on the particle is zero. The particle in a field model tells us that the magnetic force on the particle is perpendicular to both the magnetic field lines and the velocity of the particle. As the particle changes the direction of its velocity in response to the magnetic force remains perpendicular to the velocity. The particle in uniform circular motion model. The particle moves in a circle because the magnetic force is perpendicular to V and P and has a constant magnitude of QVP. The rotation is counterclockwise for a positive charge in a particle field directed into the page. If Q were negative, the rotation would be clockwise. We use the particle under a net force model to write Newton's second law for the particle. The net force will be equal to the magnetic field force, which equals ma. Because the particle moves in a circle, we model it as a particle in uniform circular motion, and we replace the acceleration with centripetal acceleration. If P would be equal to QVP, which equals mv squared divided by r. This expression leads to the following equation for the radius of the circular path. The radius will be equal to mv divided by qp. The radius of the path is proportional to the linear momentum mv of the particle and inversely proportional to the magnitude of the charge on the particle and to the magnitude of the magnetic field. The angular speed of the particle is omega, which equals v divided by r, which equals qp divided by m. The period of the motion is equal to the circumference of the circle divided by the speed of the particle. T will be equal to 2 pi r divided by v, which equals 2 pi divided by omega, which equals 2 pi m divided by qp. A charged particle having a velocity vector that has a component parallel to a uniform magnetic field moves in a helical path, as we see in this picture. V will be equal to root Vy squared plus Vz squared. Particles move in a non-uniform magnetic field. When charged particles move in a non-uniform magnetic field, the motion is complex. In a magnetic field that is strong at the ends and weak in the middle, the particles can oscillate between two positions. Now you can test yourself. And now check your answer. This is for today's concept, and thanks for your listening.